let us continue with the internal forced convection in a pipe with uniform wall heat flux condition. So in the previous video we analyzed by the order of magnitude analysis that what do you mean by thermally fully developed flow, that is the Nusselt number should be constant. Okay, that is the wall Nusselt number should be constant. So that is what we do mean by a thermally fully developed flow. Okay, and if the K is also constant, it is, if the K is not changing with temperature, then the H is also constant. Okay, now let us see that, and here we have of course considered the constant property fluid, that is, and that is why K is constant, otherwise this analysis is not valid. So now let us took the simplified equation. So what was the simplified equation? So let us go back to the previous notes. So the simplified equation was this, that is, we have the convection term, we have the axial conduction term, but for large Becquerel number that can be neglected, that I have shown several times, and that is the radial conduction. So let me write the equation here. So governing equation. Okay, so let me first write the governing equation. And that is what? That is the u z del t del z is equal to alpha 1 by r del r into r of del t del r. So this is the governing equation for large Becquerel number flow. Okay, and now if I write the boundary conditions, so the first boundary condition is, so we can think of the regularity condition. I have told you that at r equal to 0 we have del t del r equal to 0, right? And we also have at r equal to 0 q, okay, that is the heat flux. So I can write it as q at r equal to r, that is nothing but minus k del t del r at r equal to r, and that is a specified constant. Okay, and third we have something at z equal to some z naught, and at z equal to z naught we have some temperature profile, it is T equal to maybe T naught. Okay, so here I would like to bring your concentration to a fact that don't confuse with this thing, that is the direction of heat flux. So this is the pipe, okay, and these are the walls, not walls, it is a wall. So this is the radial coordinate and this is r equal to r. Okay, so whenever I am writing, maybe I am writing q, so q is the heat flux vector and the definition of that is k into grad t. Now grad t is a vector, and if I write the full expression of grad t, then this is I cap plus del t del y j cap plus del t del z k cap, right? Now you see that the direction of the heat flux is towards, so the direction of the heat flux is towards the negative gradient of T. Okay, So whenever I am writing, so this I can write minus k del t del x into I cap plus minus k del t del y into j cap plus minus k del t del z into k cap, and this I write as qx I cap plus qy. Now qx and qy and qz, these are not vectors. Qy j cap plus qz k cap. So notice that when I am writing qx, that means uh, heat flux is towards positive x direction. Okay, this is the x component of the heat flux vector. So whenever I am writing qx, this is heat flux towards positive x direction. That is, if I draw my coordinate axis like this, okay, this is x, y, z. Okay, that means I am writing, whenever I am writing qx, that means the heat flux is going from this to this direction. This is the direction of the heat flux, and that is given by minus k dt dx. If you write minus qx, that will be k into dt dx. So you have to write this minus. So I mean altogether this minus k into dt dx, if you write this, then this is having the direction towards positive x direction. Similarly, you have to write minus k del t del y, and that will denote heat flux towards positive y direction. Okay. Similarly, you will write minus k del t del z, and that will denote heat flux towards positive z direction. So one misconception is there, that is, if I am writing minus, then maybe the heat flux is towards the negative x or negative y or negative z. No. Why this minus is there? Because the change in temperature with increasing x, that should be negative. Only then the heat can flow. So this minus del t del x is indicating that the temperature is decreasing towards the increasing x. So if the temperature is decreasing towards the increasing x, that means the heat will also flow towards the increasing x. That means towards the positive x direction. Now if you write k into del t del x, that means it is k into minus of minus del t del x. In other words, I can write k into minus of del t of del of minus x. That means this temperature is decreasing towards the decreasing x, because I have here written the minus x. Minus x means towards negative direction, negative x direction, that is towards decreasing x. That means temperature is decreasing towards the decreasing x. That means the heat will also flow towards the decreasing x. And I have told all these things just to make you understand that whenever I am writing QR, so here I should write QR. So whenever let me write it clearly, whenever I am writing this Q subscript R, that means my positive heat transfer, my heat transfer is happening from the center towards the wall, that is in the increasing R direction or the positive R direction, but that will be given by this thing. Okay. Okay, so now let us take a look at this equation. So this equation, here t is a function of, okay, here t is a function of both r and z, right? And now look at the boundary condition. So this is an equation, if you compare it to your 1D transient conduction equation, okay, if you compare this with your 1D transient conduction equation, 1D transient conduction. So this is what I always encourage to you guys, that is, don't learn a problem like I am learning only this problem, because maybe the same mathematics will be applicable in the in any other physical problem, because mathematics does not understand that this is conduction, this is convection. Okay, if you have the same differential equation, then you will have the same solution, the same solution technique. Okay, so 1D transient conduction is having del t, okay, equal to alpha del t del x square. So this is the 1D transient conduction. You see that this is very similar to uh, this equation. If I term it as 1, this as 1 2a. If I term this equation as 2b and this as 2c, and maybe this as 3. So 3 is analogous to equation 1, you see that. Okay, if we have all obviously here uz, if uz is not a function of z, then it is a bit analogous. Okay, so and if you write the total energy equation, so in conduction you don't have any uh, convective term, so that is why you are only remaining with this transient term and this diffusion term. And here in the pipe flow problem you have the radial diffusion and the convective, and because it is a steady problem, the transient term is 0. Now this problem can be solved by a mathematical technique that is called separation of variable. Okay, separation of variable. But there are some more conditions that should be applied for a problem to be qualified, I mean to be qualified for being solved by separation of variable. Okay, and what are those conditions? So you should have here, obviously it is a second order equation in terms of space. Okay, so second order in space and first order in time. Okay, so you should have two BC boundary conditions in space and one boundary condition in time. Okay, out of these three boundary conditions, here you should have two homogeneous boundary conditions. Okay, and here you should have one inhomogeneous, okay, or non-homogeneous, maybe non-homogeneous boundary condition. If the equation is like this, that is the equation itself is homogeneous, okay, and then you should have two homogeneous boundary condition in space here, and you should have one non-homogeneous boundary condition in time here. Now you see that if I change this time coordinate by z, okay, and this x by r, then you will tell that well, this is a totally another problem, but that is not the case, and that is what I am trying to convey to you. That is, even if it is z and it is r, the just the independent variable are changed, but the problem is same. So in that case also, the if the problem has to be solved by the separation of variable method, then you should have one non-homogeneous boundary condition in Z and two homogeneous boundary condition in X. Okay. So you can study in detail in any good mathematics book about the separation of variables, and we will also solve one problem, one or maybe more problems by separation of variable method in convection. Okay. So now you see that in this type of problem, here we have the governing equation homogeneous, right? And we also have the second order uh, term in terms of R, second order in R, and we know the variation of uz because this is a thermally fully developed flow. So uz is equal to 2 into w average, okay, that is the average velocity in the z direction, into 1 minus r by r whole square. Okay, so uz is only a function of r. Okay, now you see the boundary conditions. In z we have a non-homogeneous boundary condition, that is true, but in r we have one homogeneous boundary condition here. So I hope you understand by that what I mean by homogeneous and non-homogeneous. Homogeneous mean that is in the RHS you are not having any term that is not dependent on R. Okay, if it is dependent on R, that is okay. Basically if you have an equation ax plus by plus cz equal to 0, then you have another equation cx plus dy plus ez equal to 0, then these are called set of homogeneous equation because the RHS is 0. Okay, so you see that the boundary condition is homogeneous for 2a, and for all, and for 2c it is non-homogeneous in the Z, but the second boundary condition for R, that is, okay, so I have written it wrongly, I apologize, and this is at wall, so it should be at R equal to capital R. Okay, but at R equal to capital R, QR, that is minus k del t del R, or in other words del t del R at R equal to R is equal to minus q by k. So this is not 0, that means this is inhomogeneous or non-homogeneous. That means this problem cannot be solved by separation of variable. Okay, so the other approach is to go for the superposition. Okay, so we can break this one problem into two problems. So two problems, each of them will have their own boundary conditions and own governing equation, and the main condition is that the governing equation of problem 1 plus the governing equation of problem 2 should give you the governing equation of the actual problem, and the boundary condition of problem 1 plus boundary condition of problem 2 should give you the actual boundary condition. So if you can break the actual problem like this, then you can solve the two separate problems, and then you can have problem 1 maybe uh, in so maybe you have broken the problem in such a manner that for problem 1 you do have the differential equation and the boundary conditions in such a form that you are able to solve that by the separation of variable method, and in the problem 2 you have a simple, maybe very simple differential equation that you can solve easily. Okay, so that also I will show you, maybe I mean that also I will show you that how can we apply the superposition in some of the problems. So here we are sure that we cannot apply the the method of separation of variable here. So what can we do? Let us see. Okay, so here in this context, now let me define something called bulk temperature or bulk mean temperature. Okay, So what is bulk mean temperature? So you see that in a pipe the fluid is flowing. Okay, the fluid is flowing like this, and it is carrying some enthalpy, right? It is carrying some enthalpy. So if you know that the average velocity is u average, okay, then you consider a control volume like this. Okay, so through this control volume, how much energy the fluid is carrying out, let us find that. Okay, so that is m dot in Cp into T, right? M dot Cp into T, because for ideal gas we can write that H is equal to Cpt. So we are considering here the ideal gas, and m dot is what? Rho into A, that is area of cross section, into U average into Cp into T. Okay, and this T here, now you see that I have written very innocently T here, but what should be this T? Because if you are having the same temperature throughout this uh, control volume, or maybe this section, I should say that that this is the energy passing through the section 1, not the control volume. So just for the time being, you take a section, not the control volume, passing through section 1, having a cross sectional area A. This is the energy, okay, passing through section 1. So let me write it: energy passing through section 1. Okay, so if I write it like this, so then what should be this T? If now this T is same for all over this section, okay, then I can write it like T. But if I have some variation of T like this, so maybe this is the variation, any kind of variation. So this is T of R, if this is the R direction. Okay, then I cannot write this T as any T. I mean, I have to define some T, right? Because I am talking about the whole area of cross section here, and throughout the whole area of cross section the T is varying. Then I am talking about which T, because I am talking about the whole energy that is being carried out by the fluid. Okay, so had I been talked about the uh, only a infinitesimal small area, okay, and through that area how much energy is being carried out, then I can have considered the T at that R location. But now I am considering the whole area. Okay, so then this T is called this bulk mean temperature. Okay, so I will take a subscript B. So this is called the bulk mean temperature. Okay, bulk mean temperature. So it is the indication of the average temperature over the cross section. Okay, so now let us relate this TB with the actual temperature profiles. So given the actual temperature profile, how can you find TB? Okay, so now let us integrate. So I have this uh, pipe, and if I draw the 3D cross section here, it will look something like this. And I can have an elemental strip, circular strip, okay, elemental circular strip that is situated at r smaller and having a thickness of dr. So through this circular strip, how much enthalpy or how much energy is being carried out? That will be my dH, let us say, that is the small enthalpy carried out through the small elemental strip. And what will be that? That will be dm dot, right, into T, into Cp into T, and this T for that T is at T equal to R. Okay, that is at this R my temperature is fixed. Okay, at a particular cross section, maybe at a particular cross section 1, my T at Tr, that is fixed. Okay, that is having something value. So now this will be what? This dm is what? Dm is rho into V, that is Vz actually. Okay, so I am writing here U. So let me change this as W average, because in this direction I am taking my velocity as W. So here also I will have my W. Okay, so this W, mind it that this W is the W value. I mean, W may be also a function of R at a particular cross section at a particular Z. So W may be also a function of R. So this W is also the W at this distance R. So this is W of R, okay, rho into velocity into area. Now what is this area? Area of this elemental strip, so that is this one, right? So that is 2 pi r into dr. Okay, I hope that is clear to you, that how this area is 2 pi r into dr. That is the circumference of this circle at r, and dr is the thickness of the elemental strip, very small strip. This is Cp T of r. Okay, so now I have to find the total enthalpy being carried out, and that is integral of Th, and that is rho W of r 2 pi r dr Cp Tr, T of r, and that is 0 to r. So you see that this term here and this term here, they should be equal, because they both of the terms are denoting the same quantity, the energy being carried out through section 1, right? So let me now write it down. Rho area of cross section W average Cp into T of bulk, that is equal to integral of 0 to r rho W of r 2 pi r. Okay, so the integral term I should write later. Sorry, CPTR. Okay, CPTR, then 2 pi r dr. So that means my TB becomes rho WR CPT of r 2 pi r dr, 0 to r, that is rho area of cross section W average Cp. Okay, so this I have got. Okay, so ideally you can see another concept. If this rho is also a function of rho r, then I should here write as rho average. Okay, but I am considering that rho is constant, and if rho is constant, then I can cut this rho out. If Cp is also constant, then I can cut this Cp out. But if Cp is also a function of r, then you have to again integrate Ct, and in the denominator you have to write Cp average. Okay, so this boils down to 0 to r wr tr 2 pi r dr. Okay, and this is area into w average. Okay, now you see that this is the specific definition for cylindrical coordinate. So what if anyone asks you that that the same problem, I can give you the internal force convection between two parallel plates, then how can you solve it? if then you if then you tell that I knew the bulk mean temperature concept in the cylindrical coordinate, but I don't know in the uh, in the Cartesian coordinate. I knew it for the pipe, but I don't know for the parallel plate channel. Then I mean, how can you not know? Because you know because you know the concept, that the bulk mean temperature concept comes from this thing, that is the total energy passing through any area, I mean any cross section. So here what will be this thing? I will tell you the answer, but your homework will be to figure out how that is so. So this 2 pi r dr here, it is nothing but the area dA. Okay, this is nothing but the dA. So in the Cartesian coordinate this will be b into dx, that is b is the width of the parallel plates, if that is so. I think this is clear. Okay, because this 2 pi r dr, I have already told you the answer, that is you don't have to think now also. So this is the actually the dA of the elemental strip. So in the parallel plate channel, if the cross section is like this, then you take a strip like this. So here this is b, and this is dx at a distance x, or dy maybe. So that is b dx. Okay, then you can find that. So this is the bulk mean temperature. Okay, now from the same concept, if you define bulk of any property, so let p be a capital P be a arbitrary property. So bulk mean of p will be wr p of r 2 pi r dr a into w average. Okay, so now you know that this is your bulk mean operator, that is this one wr, here the main quantity 2 pi r dr by a into w average, but this 2 pi r dr is only for the cylindrical coordinate. Okay, so now I have told you this bulk mean temperature concept, right? So now you tell me that this Tb is a function of what? This Tb is a function of only z, because for this problem, for this pipe flow problem, this T is a function of both r and z. But to find Tb, you have integrated this T over r, right? You have integrated this T over r, and that is how you got the bulk mean temperature. That means this is not the, and as this is a fine definite integral, so this Tb is no more a function of r, it is only a function of z. Okay, it is only a function of z. So now if you define something like a variable phi equals to t minus tb, then that will be okay. So you have defined, so let me write it uh, properly. So define phi equal to t minus tb. Okay, so if phi equal to t minus tb, then what will be phi b? So phi b will be integral of t minus tb w of r. Obviously I am not writing the of r thing again. Okay, and 2 pi r dr by w average and into area, right? And that is you can write it obviously 0 to r. So this is 0 to r T of this thing by W average into area minus 0 to r TB W 2 pi r dr by W average into area. Now what is this? Can you recognize this? This is nothing but your TB, right? Bulk mean temperature. And what is this? How can you find this? This TB is only a function of z, right, and not a function of r. Then you can take out this of integral. So this becomes TB into integral 0 to r W 2 pi r dr, right? W average into area. Now if I take the same concept for the mass, that is at any cross section, what should be the mass flow rate? That is the rho into W average into area. And what should be the mass flow rate in terms of the actual W? That is integral of rho into dA, that is the small elemental area, into the local W, right? And if the rho is constant, so then this can be cancelled out. And in the Cartesian coordinate, I can write this as W average into area into W into 2 pi r dr, because in in cylindrical coordinate dI is 2 pi r dr. So W average into A equal to integral of 0 to 2 r, integral 0 to r W into 2 pi r dr. So that means this term here sorry sorry this term here is 1, so this becomes TB. So both this term is TB, this term is TB, that means this is 0. Okay, so that means phi b is equal to 0 at any z. Okay, this is a very important conclusion. Okay, so phi b equal to 0 at any z, that means d phi b dz, that is equal to 0. But you see that d dB dz is equal to 0. Can we say that? We cannot say that. I have told you TV is a function of z and not a function of r only. I can write this, that is equal to 0, but dTB dz equal to 0, that we cannot write. But d phi b dz is equal to 0, right? That means now phi b is also, I mean, uh, before saying this that phi b equal to 0 at any z, I have already the fact that phi b is only a function of z and not a function of r. I have this thing already. That means now if I say that this phi b is 0, okay, that means phi b is not changing with z. Okay, and phi b is also not a function of r. Okay, so now here I will talk about a very important conclusion. Now in the pipe, okay, I have the local variable phi. So phi is what? T minus TB. So phi is a function of r comma z. Okay, phi is a function of r comma z, and because t is also a function of r comma z, and TB is a function of z only, right? So phi is a function of r comma z. So at any section, this section 1, section 2, section 3. So at any section, if I have to calculate phi, then this phi will vary over the r, but this variation of phi over the r, so maybe here this phi is a particular function, that is phi of 1, phi at section 1, this is g of r, and here it is phi of 2 and this is h of r, and here it is phi of 3, it is k of r. Okay, so at any section I can say that phi may be any other variation of r, right? But now I have told that this phi b, that is only a function of z. Okay, so if phi b, So if phi 1, phi 2 and phi 3 are different, then okay, then uh, okay, so now you see that here I can have two options. That is, if I integrate this phi 1 over the r, this coordinate, then this integral phi of r may be equal to integral phi of 2 into dr, may be equal to integral of phi of 3 into dr. I cannot say that if it is compulsory or not. That is the integration of phi with respect to r, okay, or maybe any weighted integration like w into w, okay. And if it is weighted integration into w into 2 pi into w into 2 pi, then it becomes the bulk, okay. So bulk mean phi, that is the averaged over r, averaged over the cross section, okay. So if the averaged over the cross section, that thing is changing with the axial direction, then you surely, I mean, then you are sure that this phi is having a z, this phi is having a z dependence, okay. So am I clear about that? Because okay, so if I can give you a real life analogy, a beautiful analogy, okay. So this phi b is the averaged quantity over r, averaged quantity over r, okay. Okay, so I got the analogy. Let us say that we have 5 people at every cross section. At every cross section we have 5 people, okay, and each people are having some number of apples maybe. So this people is having maybe 1, this is 2, this is 4, this is 0, this is 10, and this people is having like 2, this is 4, this is 1, this is 10, this is 0, and this people maybe is having an apple similar to this 1, 2, 4, 0, 10. So here these 5 peoples are having different number of apples at different counters, counters 1, 2 and 3. Now you see that if you see this counter and this counter, then the distribution of apple are identical, but at this counter, okay, so but at this counter and the second counter, the counter 1 and 2, the distributions are not identical, but the average number of apples at counter 1 and counter 2, they are equal, right? So my point is, if the average number of apples are equal at both the counters, then there is a possibility that the distribution of the apples are also equal. But now if you are having another counter, maybe the 0th counter, but now you are having something like this, 5 people are there obviously, but now the numbers of apple are 100, 0, 30, 41, 3. So now you can see that clearly this average number of apples here is not matching with average number of apples here. Then you can surely know that the distribution of apple at counter 1 is equal to the distribution of apple at counter 0. Similarly, if phi b is not a function of z, then that implies we can have a phi that is the local phi, and that is also a function of r only. That is phi is not a function of z. We can have, I have not told that we will have, we can have, there is a possibility. But uh, but if but if we know that phi b is varying with z, then for sure we cannot have Okay, for sure that we cannot have phi is only a function of r. Phi must be a function of r comma z. Okay, so I hope that I am clear. Okay, I have tried to convey this concept because this is the crux of the next part that I will do. So now I have seen that my phi b is 0 for all z. That means phi b is not a function of z, right? So then I have a possibility that phi will also not be a function of z. That is, phi will only be a function of r. So let us try to find, let us try to find a solution phi equal to phi of r, okay, of a equation of the following equation. And what will be the equation? Can you guess it? Of the following equation. That is, I have defined phi equal to t minus tb. I have the equation that is uz, that is nothing but 2 into w average into 1 minus 1 by r square into del t del z is equal to alpha 1 by r del t del r, okay, into r into dt dr. Okay, now here I define phi equal to t minus tb and eta equal to r by r. So then this equation becomes, I have done ample amount of times these types of transformation, so I will not do it again. Okay, so this will be 1 minus eta square, so del t del z. So you can see that tb is not a so okay, so here it will be what, del b del phi del z, okay, del phi del z plus del tb del z, right? Because you see from here t is equal to phi plus tb, so del t del z equal to this, okay, and that is equal to alpha into 1 by, so instead of r we will write eta 1 by eta, okay, del eta eta. Now same thing here also you will have del phi del r plus del tb del r, okay, okay, now it is fine. Now you see that tb is already averaged over r, so then del tb del r is 0, okay, and here tb is already averaged over r, so del tb del z is nothing but dtb dz. Now can we find this? Okay, so dtb dz we will find it later, but now I have told you, can we find a solution phi equal to phi of r only? So if phi equal to, so we are trying to solve it. So assume, we are assuming, okay, so we are assuming phi equal to phi of r only. So if we assume that, then this boils down to 0. So then the equation boils down to w average 1 minus eta square into what, into dtv dz, that is equal to alpha 1 by eta, now it will be dd eta, right? Okay, so del phi del r, I have made some mistake during the transformation. So when I will transform this, here I will have 1 eta 1 eta 1 eta, another eta here, another eta here. Now you see that for every eta I have to multiply 1 r, 1 capital R, Why? Because eta is equal to r by r. So uh, del r or dr is equal to r into d eta. So for every del eta, or also uh, r equal to eta into r. So for every eta or every del eta, because dr is equal to r into d eta, also r equal to r into eta. So for every d eta and every eta, I have to multiply 1 r. Okay. Okay. So I will multiply 1 r here, 1 r above, and again 1 by r, again 1 r here. So 1 r and 1 r cancel out, and 1 by r square will be there. So alpha by r square will be there. Alpha by r square 1 by eta d eta, okay, into eta, okay, into d phi d eta. Okay. So I think I have not done any mistake in writing this term. So let me just break it down, then I can understand. So this will be this into this, the first order term, plus the second order term. Okay, I have not made any mistake. It is fine. Okay, so this is the equation. Okay, this is the equation. So we will see. Okay, so now I will stop here. Okay, I will stop here, and I will continue with the solution of this thing. Okay, I have told you that I will solve this equation and with the boundary conditions, but there is a catch with the boundary condition, and I have already given you the hint. I am giving you some more hint, so that you can think about the future steps. I have told you that we cannot solve the actual problem, this problem, with the method of separation of variable. Okay, with the method of separation of variable, that is this problem, and that is because we are not having two homogeneous boundary conditions. One boundary condition is inhomogeneous for the r coordinate. So can you break this problem into two problems, for which one problem will have two homogeneous boundary condition for r and one non-homogeneous boundary condition for z, and the other and the other and the and similarly we will get the other boundary condition also. Okay, so now if I can break this problem, that is t equal to some my, okay, so t equal to tb plus phi I have there. Now if I can break this problem, phi equal to capital Phi plus some psi, because eta I have already used. Okay, some psi. Okay, okay, then I can have t equal to tb plus phi plus psi. Okay, so then I can break this problem into three problems having three governing variables. Okay, and this phi is having the boundary condition this. So I have break this boundary condition also into two different problems. Okay, so I will talk about it. I will talk about it later, because I understand that this is becoming more hard to you. But up till it, I think you have understood, right? Because I will try to find the solution of phi such that this phi is only a function of r, and if this phi is only a function of r, so then this term boils down to 0. And let us try to solve this equation in the next discussion. Okay, and until then, bye and take care. Okay, so let us meet in the next discussion. Goodbye, take care, and thank you.